Before we begin, please remember that this video is for educational and informational purposes only. The concepts discussed are foundational in computer science, and any actions you take based on this information are at your own discretion. Always ensure you are complying with software licensing agreements and terms of service. Have you ever downloaded a file from the internet and felt that split second of panic right before you double-click it? That feeling of, is this going to be the thing that messes up my entire computer? What if you could open that sketchy file, run that weird, untrusted program, or even unleash a computer virus on purpose, and your actual computer would be completely 100% perfectly safe? Like detonating a bomb inside a titanium-lined vault. When you're done, you just close the vault door, and the chaos inside simply vanishes. Your real machine is untouched, unharmed, and doesn't even know anything happened. This isn't science fiction. This is a real, accessible technology that you can use on the very computer you're using to watch this video. And it's called a virtual machine. But it's so much more than just a digital safety net. Imagine you own a MacBook, but you absolutely need to run a specific program that only exists for Windows. Do you have to go out and buy a whole new PC? No. With a virtual machine, you can run a full version of Windows right on your Mac inside its own window. You can drag and drop files between them. You can have macOS and Windows running side by side at the same time on the same screen. This is the power we're unlocking today. By the end of this video, you are going to understand in simple, plain English exactly what a virtual machine is. You'll know how this computer inside a computer actually works, and you'll discover real-world reasons you might want to start using one right away, for security, for software testing, or just to explore a completely new operating system without any risk. We're going to demystify this powerful piece of tech that, believe it or not, is the fundamental building block of the entire modern internet and cloud computing as we know it. So let's get right to it. What exactly is a virtual machine? The simplest way to think about it is this. A virtual machine, or VM for short, is an emulation of a computer system. It's a software-based computer that runs on your physical computer. Let's break that down with an analogy. Think of your physical computer, your laptop or your desktop, as a large physical building. This building has essential utilities. It has an electrical system, which we can call the CPU or the processor. It has a water supply, let's call that the RAM or memory. It has rooms and storage closets, which are your hard drive space. And it has an internet connection, your network card. This is your real hardware. It's the physical foundation. Now, you want to rent out a part of your building. You don't want to give the tenant a random collection of pipes and wires. You want to give them a complete, self-contained apartment. So you build walls, you run new plumbing and wiring that taps into the main building supply, and you create a fully functional, isolated living space inside your larger building. It has its own little kitchen, its own bathroom, its own bedroom. It uses the building's main electricity and water, but it has its own circuit breakers and its own faucets. The tenant living in that apartment can paint the walls whatever color they want, make a huge mess, or even have a wild party, and none of it affects your part of the building. The walls are soundproof, the plumbing is separate. It is its own isolated world. That apartment is a virtual machine. Your physical computer is called the host. It's the building. The virtual machine is called the guest. It's the apartment. The guest borrows resources from the host. When you create a new virtual machine, you get to decide how big its apartment is. You might say, okay, my laptop has 16 gigabytes of RAM. I'm going to lend 4 gigabytes to this virtual machine. My processor has 8 cores. I'll let the VM use 2 of them. And my hard drive has 1 terabyte of space. I'll give the VM a 50 gigabyte virtual hard drive. So the VM runs as a self-contained unit, using a portion of your real computer's power. To the virtual machine, it doesn't know it's a guest. It believes it is a real physical computer. When you install an operating system on it like Windows or Linux, that operating system believes it has its own dedicated processor, its own dedicated memory, and its own dedicated hard drive. It has no idea it's living inside a window on your main computer. This creates that perfect isolation. If you download a virus inside the virtual machine, it can only affect the virtual machine's apartment. It can't break through the walls and infect your main host computer. When you're done, you can just delete the entire virtual machine, which is really just a collection of big files on your host computer. It's like demolishing the apartment and having the space back perfectly clean. Now you might be asking, okay, that makes sense. But what is the magic software that acts as the architect? What's building these digital walls and managing the flow of electricity and water between the building and the apartment? That is the most important piece of the puzzle, and it's called a hypervisor. The hypervisor is the property manager of your building. It's a layer of software that sits between your physical hardware, the host, and the virtual machine, the guest. Its job is to create, run, and manage the virtual machines. It's the program that carves out a slice of your real CPU, a chunk of your real RAM, and a piece of your real hard drive, and presents it to the guest OS as a complete, believable package of hardware. There are two main types of hypervisors, but for today we're focused on the one you'd use on your personal computer. These are applications you can install just like any other program. Popular ones you may have heard of are VirtualBox, which is free and open source, VMware Workstation Player or Fusion, and Parallels for Mac. You install one of these programs, and suddenly, your computer has the superpower to create other computers inside of itself. So let's recap the key players. You have the host, which is your physical laptop or desktop. You have the guest, which is the virtual machine, the complete but simulated computer running in a window. And you have the hypervisor, the software that makes it all possible by managing the resources and creating that crucial layer of isolation. This isn't just a neat party trick for tech enthusiasts. This concept of isolating systems and running multiple apartments on a single powerful building is the bedrock of the modern digital world. Every time you watch a Netflix show, use a Google Doc, or scroll through Instagram, you are interacting with services that are almost certainly running on thousands upon thousands of virtual machines, all humming away in massive data centers owned by companies like Amazon, Google, and Microsoft. They don't buy a separate physical server for every single customer. Instead, they buy incredibly powerful host servers, massive buildings, and then use a hypervisor to create hundreds of secure, isolated virtual machine apartments that they rent out to their customers. It's efficient, it's scalable, and it's secure, all thanks to the principles we're talking about right now. But how? How does a hypervisor actually do this? How does it trick a massive, complex operating system like Windows 11 into believing it's running on real metal when it's actually just a clever illusion? The answer lies in a special set of instructions built directly into modern processors from companies like Intel and AMD, a kind of hardware-level superpower that makes this entire process incredibly fast and efficient. It's a fascinating story of how hardware and software work together to create something that feels like magic. And that's exactly what we're diving into next. To understand this superpower, we have to rewind the clock a bit, back to a time before virtual machines were everywhere. Imagine a world not too long ago where one powerful computer could only do one thing at a time. You'd buy a massive, expensive server, a real beast of a machine with a powerful processor, tons of memory, and huge storage. And what would you run on it? Maybe just a single company website, or a database, or an email server. That's it. The entire thundering power of that machine was dedicated to one single job. It was like hiring a world-class Michelin star chef, capable of preparing a 10-course tasting menu for 100 people, and telling them their only job all day, every day is to make toast. Just toast. The chef would be bored out of their mind, and you'd be wasting an incredible amount of talent and money. That was the state of computing for a long time. Companies had server rooms filled with these underutilized machines, each one running at maybe 5 or 10% of its total capacity. It was incredibly inefficient. A huge waste of electricity, cooling, and physical space. Computer scientists saw this problem and came up with a brilliant, almost deceptive idea. What if we could trick the computer? What if we could install a special piece of software, a clever manager, that could slice up the server's resources, the processor, the memory, the storage, and pretend that it was actually several different smaller computers? This clever manager program was called a hypervisor. The hypervisor would sit between the physical hardware and the operating systems. Its job was to be the ultimate puppet master. It would present a fake virtual set of hardware to each operating system you wanted to run. So, you could install Windows in one virtual machine, and a version of Linux in another, both on the same physical box. To Windows, it looked like it had its own dedicated computer. To Linux, it also looked like it had its own dedicated computer. Neither of them knew the other existed. They were living in their own little matrix, and the hypervisor was the architect. This was a revolutionary idea. Suddenly, that one giant server, that one brilliant chef, could now cook multiple dishes at once. It could run the website, the database, and the email server all at the same time. The efficiency gains were massive. But there was a catch. A big one. This early form of virtualization was done entirely in software. The computer's main brain, the CPU, had no idea this was happening. It was designed to work for one boss, one operating system. The hypervisor had to perform a constant, exhausting translation job. Every time a guest operating system like Windows wanted to do something that required direct access to the hardware, a privileged instruction, the hypervisor had to jump in, intercept the request, check it to make sure it wouldn't mess with the other virtual machines, translate it into something the real hardware could understand, and then pass it along. Then it would have to take the hardware's response, translate it back, and give it to the Windows virtual machine, which was none the wiser. Think of our chef again. It's like the head chef, the hypervisor, is giving instructions to a chef, the CPU, who only speaks English. But one of the recipes is in French and another is in Japanese. The head chef has to constantly translate line by line. Okay chef, the French recipe says sauté les oignons. That means you need to gently fry the onions. Now do that. Okay, you're done. Great. Now the Japanese recipe says komo togu. That means you need to wash the rice. This constant translation creates a ton of overhead. Slows everything down. The chef is spending more time listening to translations than actually cooking. Virtual machines worked, but they were often sluggish and couldn't handle really demanding tasks. They were a clever trick, but not a perfect solution. This is where the story takes a turn. This is where the magic happens. The two biggest CPU manufacturers in the world, Intel and AMD, saw what was happening. They saw the future. They realized that virtualization wasn't just a niche trick. It was the future of computing. So they asked a profound question. What if the CPU didn't have to be tricked? What if we could teach the chef to speak French and Japanese directly? They decided to build the tools for virtualization right into the silicon of the processor itself. They added a whole new set of instructions, a secret language, specifically for running virtual machines. Intel called their technology VTX. AMD called theirs AMDV. And this changed everything. This was the hardware-level superpower. To understand how profound this was, we need a quick lesson on how a CPU works. Think of it like a highly secure government building with different levels of clearance. At the very center, the most secure, most powerful level, is called Ring 0. This is the VIP lounge, the command center. This is where the core of the operating system, the kernel, lives. It has ultimate power and can talk directly to the hardware. All your normal applications, like your web browser or a video game, live in a less privileged area, usually called Ring 3. They are not allowed in the VIP lounge. If they need anything from the hardware, they have to politely ask the kernel in Ring 0 to do it for them. In the old days of software virtualization, the hypervisor and all the guest operating systems had to fight over who got to be in the single, all-powerful Ring 0. It was a messy, complicated struggle that created all that performance-killing overhead. But with hardware virtualization like VTX and AMDV, the CPU manufacturers did something genius. They built a new, even more powerful foundation beneath everything else. A sort of Ring -1. A super-secret basement command bunker that is even more privileged than Ring 0. Now the hypervisor, our puppet master, gets to live in this new all-powerful Ring -1. It is the undisputed king of the machine. From there, it can create multiple separate virtual VIP lounges, multiple Ring 0s. It then invites each guest operating system into its own private, sandboxed Ring 0. The Windows virtual machine gets a Ring 0. The Linux virtual machine gets a Ring 0. They each think they are the boss, the sole ruler of the hardware. They can issue their privileged commands without even realizing they are inside a simulation. Because this is all built into the hardware, the CPU itself knows what's going on. When the virtual Windows machine issues a command, the CPU doesn't have to be tricked by the hypervisor. The CPU's own internal logic knows, this command is from virtual machine A. I need to handle it within its designated slice of memory and resources. And I must make sure it doesn't interfere with virtual machine B. The translation step is gone. The head chef no longer needs to translate. They just hand the French recipe directly to the chef, who now understands French perfectly. The process became incredibly fast. The performance penalty, the overhead of virtualization, practically vanished overnight. Virtual machines were no longer slow, clunky novelties. They were now lean, mean, and almost as fast as running on the bare metal hardware itself. This single innovation is what unlocked the modern cloud computing era. It's what allows companies like Amazon, Google, and Microsoft to run millions of virtual servers for millions of customers on a massive, efficient scale. It's what allows a developer to test their new app on Windows, macOS, and Linux, all at the same time, on a single laptop. Its security, its efficiency, its flexibility, all made possible because the chipmakers decided to build a hypervisor's dream tools directly into the processor. So now we have this incredible power, this hardware-assisted ability to create near-perfect digital copies of a computer. But how is this power actually used? Turns out there isn't just one way to be a hypervisor. There are two major approaches, two distinct philosophies on how to manage these virtual worlds. One is built for massive industrial-scale data centers. The other is designed for your personal desktop or laptop. They are known as Type 1 and Type 2 hypervisors, and understanding the difference between them is the key to understanding where and why we use virtual machines in our daily lives. Let's start with the first one, the big one, the engine of the modern internet, the Type 1 hypervisor. The industry has a cooler name for it, though, a bare metal hypervisor. And that name tells you everything you need to know. When we say bare metal, we mean it runs directly on the computer's physical hardware. There is no other operating system underneath it. It is the first thing that boots up when you press the power button. Think of it like building a skyscraper. A Type 1 hypervisor is the foundation poured directly onto the bedrock. It's not an app you install. It is the base layer of the entire system. Imagine you're a world-class orchestra conductor. The musicians and their instruments, the violins, the cellos, the brass, the percussion, that's your computer's hardware. The CPU, the memory, the storage. As the conductor, you don't need to ask a stage manager for permission to tell the violins to play louder. You have direct, absolute control over every single instrument. You can make them play one beautiful symphony, or you can split them up, having one section play a classical piece while another section simultaneously plays a jazz arrangement. You are managing all the resources directly for maximum performance. That's exactly what a Type 1 hypervisor does. It has a privileged, direct line to all the physical hardware. This direct access means it's incredibly fast and efficient. There's no middleman. There's no bloated, general-purpose operating system like Windows or macOS underneath it, using up precious memory and CPU cycles just to run a desktop background or a start menu. The Type 1 hypervisor's only job, its entire reason for existence, is to do one thing and do it perfectly: create, run, and manage virtual machines as efficiently as humanly possible. Because of this raw power and efficiency, Type 1 hypervisors are the undisputed kings of the data center. This is the technology that powers the cloud. When you hear about Amazon Web Services or Google Cloud or Microsoft Azure, you are hearing about massive global networks of servers running Type 1 hypervisors. Companies like Netflix aren't mailing you a DVD anymore. They are running their entire streaming service on thousands of virtual machines, spun up and down on demand, inside these cloud data centers. The website you're on right now, the app you'll use later, the game servers you connect to, chances are, they are all living inside a virtual machine managed by a Type 1 hypervisor. Popular examples of this technology are VMware's ESXi, Microsoft's Hyper-V, and the open-source KVM, which is built into the Linux kernel. They are the invisible, powerful workhorses of our digital world. But what if you're not a multi-billion-dollar corporation running a global data center? What if you're a software developer, a cybersecurity student, or just a tech enthusiast who wants to run a different operating system without buying a whole new computer? You don't need the industrial strength, bare metal solution. You need something simpler, something that works on the computer you already have. This is where our second category comes in, the Type 2 hypervisor. If a Type 1 hypervisor is the foundation of a skyscraper, a Type 2 hypervisor is more like a prefabricated room that you place inside an existing house. It's also known as a hosted hypervisor, and that name is just as descriptive. It's hosted because it runs as a regular piece of software, a normal application, on top of your existing operating system. You install it just like you would install a web browser or a video game. You have your Windows PC or your Mac, you go to a website, you download the installer, you click next a few times, and boom, you have a program that lets you create virtual machines. Let's go back to our analogies. A Type 2 hypervisor isn't the orchestra conductor. Instead, imagine your main operating system. Let's say it's Windows, is the concert hall itself. It has its own rules, its own staff, its own acoustics. The Type 2 hypervisor is like a band-in-a-box program you run on a laptop on the stage. Inside that program, you can create and play virtual instruments. But that program doesn't have direct control over the concert hall's main lighting or sound system. It has to ask the concert hall's manager, your Windows operating system, for everything it needs. Hey Windows, can I please have some electricity for my virtual keyboard? Can I have some space on the stage for my virtual drum kit? This is the key difference. The Type 2 hypervisor has to go through your main OS, the host OS, to get to the physical hardware. This creates an extra layer of translation and management. Your host operating system needs its own share of the computer's resources to run itself, and then the hypervisor application needs resources, and then the virtual machines you run inside it, the guest operating systems, need resources. It's a chain of command, and this chain introduces overhead. It means a virtual machine running on a Type 2 hypervisor will never be quite as fast or efficient as one running on a Type 1. But what you lose in raw performance, you gain in convenience and accessibility. It is unbelievably easy to get started. This is the world of desktop virtualization. The most famous names here are Oracle's VirtualBox, which is completely free and incredibly popular with students and hobbyists. Then there's VMware Workstation for Windows and Linux, and VMware Fusion for Mac. For Mac users who want the best possible experience running Windows, Parallels Desktop is a legendary piece of software. With these programs, you can be running Windows, open the application, and within minutes, have a full-blown version of Ubuntu Linux running in a window on your desktop. You can copy and paste between them. You can drag and drop files. Feels like magic. This is perfect for a developer who needs to test their application on multiple operating systems without owning 3 different computers. It's a lifesaver for a cybersecurity analyst who needs a safe, isolated sandbox to open a suspicious file without risking their main computer. It's an incredible tool for anyone who's just curious and wants to explore a new operating system without the commitment of wiping their hard drive and starting from scratch. So let's put it all together. Type 1, the bare metal hypervisor, installs directly on the hardware. It is the foundation. It offers maximum performance and is the engine of the cloud and enterprise data centers. Think efficiency, power, and scale. Type 2, the hosted hypervisor, runs as an application on your existing operating system. It is a program you install. It offers maximum convenience and is the perfect tool for desktop use, development, and testing. Think flexibility, ease of use, and accessibility. One is for running the internet's infrastructure. The other is for running a different world inside a window on your laptop. Understanding this distinction is crucial because it frames the entire conversation about why we even bother with this stuff. We now know the what. A virtual machine is a computer inside a computer. And we know the how. They are created and managed by a special piece of software called a hypervisor, which comes in 2 main flavors. But this all leads to the most important question of all. What's the point? Why go through all this trouble to create these digital ghosts of computers? The answer isn't just a single thing. It's a collection of powerful advantages that have fundamentally reshaped the world of technology, from saving companies millions of dollars to keeping your personal computer safe. Let's start with the biggest, most earth-shaking advantage, the one that completely changed the game for businesses big and small. To understand its impact, we need to take a quick trip back in time to the dark ages of IT, say the late 1990s or early 2000s. Imagine you're running a growing online business. You have a website. That website needs to live on a computer, a special powerful computer called a server. Simple enough. But then you also need a server just for your company's email, and another one to store all your customer data in a database, and another one to handle your internal files, and another for your accounting software. Very quickly you have a problem. You have a room, then a bigger room, then an entire floor of your building filled with these big, loud, hot, power-hungry beige boxes. Each box is a physical server, and each server is dedicated to doing just one thing. This was the reality. It was called server sprawl, and it was a nightmare. Look at one of those servers. Its processor, its brain, is probably only using about 10 or 15% of its total power. The rest of it? It's just sitting there idle doing nothing. But you're still paying for 100% of it. You're paying for the electricity to run it 24/7. You're paying for the massive air conditioning systems to keep that room from melting. You're paying for the physical space it takes up, the expensive square footage. You're paying for the network cables, the power strips, the racks to hold them. You are literally burning mountains of cash to power a graveyard of underused machines. And when you needed a new application, you had to go through the whole painful process again. Order a new physical server, wait weeks for it to arrive, find a place to rack it, wire it up, install the operating system from scratch. It was slow, inefficient, and astronomically expensive. This is the monster that virtual machines were born to slay. This is advantage number 1. Consolidation. Instead of having 20 different physical servers, each using only a tiny fraction of their potential, what if you could buy just one really powerful physical server? And then, inside that one box, you create 20 virtual machines. Suddenly, VM number 1 is your web server. VM number 2 is your email server. VM number 3 is your database. Each one thinks it's on its own private hardware, But really, they're all just cleverly sharing the resources of that single powerful machine. It's like the difference between building 20 separate little houses for 20 people versus building one large, efficient apartment building. Instead of 20 separate roofs, 20 separate heating systems, and 20 separate plots of land, you have one building, sharing resources, managed from a central point. The cost savings are staggering. Companies went from needing entire data centers the size of warehouses down to a few simple racks of servers. The reduction in hardware costs, electricity bills, cooling costs, and physical footprint wasn't just a small improvement. It was a revolution. It saved businesses billions of dollars and completely redefined how computing infrastructure was built. That one powerful server can now run its processor at 70, 80, or even 90% capacity, efficiently parceling out its power to all the VMs that need it. The waste is virtually eliminated, but saving money is just the beginning. Let's talk about something even more critical: safety. This brings us to the second massive advantage: isolation. Think of each virtual machine as its own impenetrable, soundproof room. What happens in one room stays in one room. Let's bring this down to a personal level. Have you ever gotten an email with a weird attachment from someone you don't quite trust? Or maybe you wanted to download a piece of free software from a website that looked a little sketchy. The old you would have to make a choice. Risk infecting your entire computer, your precious photos, your banking information, your life, or just miss out. With a virtual machine, you don't have to choose. You can create a disposable Windows or Linux virtual machine on your main computer. It's a completely sealed-off sandbox. You fire up that VM, you go to that sketchy website, you download that weird file, you run that questionable program. And let's say it's a trap. A nasty virus springs to life and starts trying to wreck everything. Here's the beautiful part. It can't. It's trapped inside the virtual machine. It's like a tiger in a cage. It can roar and claw at the bars all it wants, but it cannot touch your actual physical computer. The virus might completely destroy the virtual machine's virtual hard drive, but your real hard drive, with your family photos and important documents, is completely unaffected. It's sitting outside the cage, perfectly safe. When you're done with your experiment, you can just delete the entire virtual machine. Poof! The cage, the tiger, and all the destruction it caused are gone forever, as if they never existed. This principle of isolation is a cornerstone of modern cybersecurity. It allows researchers to safely detonate and study malware. It allows developers to test new, unstable code without crashing their primary systems. For you, it's a digital laboratory, a quarantine zone where you can experiment without fear. Okay, so they save money and they provide a safety bubble. What else? Let's get to the part that feels like actual magic. Advantage number 3, portability. What is a physical computer? It's a heavy box of metal and plastic, filled with delicate components and tethered to a wall by a nest of cables. If you want to move it, it's a whole ordeal. You have to shut it down, unplug everything, lug it across the room or across the country, plug it all back in, and pray everything still works. Now, what is a virtual machine? At its core, it's just a handful of files on your hard drive. That's it. Your entire virtual computer, the virtual hard disk, the virtual memory, the virtual settings, it's all encapsulated in a few files that you can see in a folder. What does this mean? It means you can move an entire computer the same way you move a photo or a text document. You can copy it. You can back it up to an external drive. You could, in theory, upload it to cloud storage or even email it to a colleague if the files weren't so large. Imagine taking that entire perfectly configured web server VM we talked about and just dragging and dropping it from one physical host machine to another, even while it's running with zero downtime. This is not science fiction. This happens millions of times a day in data centers around the world. This level of portability is impossible with physical hardware. It gives you a fluidity, a flexibility that is simply revolutionary. This leads directly into our fourth, and perhaps my favorite advantage: snapshots. Anyone who's ever played a video game understands the concept of a save point. You're about to fight a big scary boss, so you save your game. If the fight goes badly, you don't have to start the entire game over. You just reload from your save point, and you're right back where you were seconds before the battle, ready to try again. A snapshot in a virtual machine is exactly that, but for an entire computer. Imagine you're about to perform a major, risky software update on a critical server. Or maybe on your personal computer, you're about to install some complex new program, and you're not sure if it will mess up your other settings. Before you do anything, you click a button. Take snapshot. In a few seconds, the virtualization software takes a perfect picture of the entire state of your VM at that exact moment in time. Now you proceed with the update, and it's a disaster. Everything crashes. The new software conflicts with the old software, data gets corrupted, nothing works. In the physical world, you'd be facing hours, maybe days of painstaking work trying to uninstall things, fix the registry, and restore from a clunky backup. It would be a nightmare. In the virtual world, you just click revert to snapshot. And in the blink of an eye, your entire virtual machine is instantly transported back in time to the exact moment before you made the change. The catastrophic update never happened. The corrupted data is gone. Everything is exactly as it was. It is the ultimate undo button. It's a time machine for your computer. This single feature has saved countless hours of work and prevented untold numbers of disasters, giving people the freedom to experiment and innovate without the fear of irreversible consequences. So we have incredible cost savings through consolidation, a bulletproof safety net through isolation, unbelievable flexibility through portability, and a time machine with snapshots. These aren't just minor perks, they are fundamental shifts in what we can do with computers, how we manage them, and how we protect them. But this all begs a very important question. How? How is any of this actually possible? What is the secret sauce? The layer of software magic that sits between the physical hardware and these virtual worlds, conducting this entire orchestra. That conductor, that master of ceremonies, has a name. In the world of computing, we call it the hypervisor. It might sound like a term from a science fiction movie, but its job is surprisingly down to earth. The hypervisor is the special foundational software that creates and runs virtual machines. It is the puppet master, and the virtual machines are its puppets. Its entire purpose in life is to manage the host computer's resources, the processor, the memory, the storage, and distribute them among all the different guest virtual machines that want to use them. Think of the hypervisor as the ultimate, hyper-efficient property manager of an apartment building. The physical computer is the building itself. It has a certain amount of electricity, a certain amount of water, a certain amount of plumbing. Each virtual machine is a tenant renting an apartment. One tenant might need a small studio with minimal water and electricity. That's our lightweight Linux server. Another tenant might rent a massive, multi-floor penthouse, needing tons of power and resources. That's our heavy-duty Windows development environment. The hypervisor is the manager who installs the meters, divides the utility lines, and hands out the keys. It makes sure the Linux tenant in 2B can't tap into the water supply for the Windows tenant in the penthouse. It ensures that if one tenant throws a wild party and overloads their circuit breaker, it doesn't black out the entire building. The hypervisor provides this crucial layer of isolation and management, allowing multiple tenants, multiple operating systems, to coexist peacefully and safely on a single piece of property, a single piece of hardware. Now this is where it gets really interesting. Not all property managers and not all hypervisors are built the same way. They generally fall into two major categories, and understanding the difference is key to understanding the entire world of virtualization. We call them Type 1 and Type 2. First, let's talk about the big guns, the Type 1 hypervisor. This is also known as a bare metal hypervisor. The name tells you everything you need to know. It installs directly onto the computer's raw physical hardware, the bare metal. There is no other operating system underneath it. The hypervisor is the operating system. This is the foundation of the entire building. It's the first thing you pour after you've dug the hole. Because it sits directly on the hardware, it is incredibly lean, efficient, and fast. It doesn't have to compete for resources with the host operating system, because there isn't one. All of its energy is dedicated to one thing: running virtual machines as efficiently as humanly possible. This is the kind of hypervisor that powers the cloud. Companies like Amazon, Google, and Microsoft use Type 1 hypervisors across millions of servers in their massive data centers. When you spin up a server on AWS, you're using a virtual machine running on a powerful bare metal hypervisor. It's built for performance, stability, and security at a massive scale. Then you have the Type 2 hypervisor, also known as a hosted hypervisor. If a Type 1 is the foundation of the building, a Type 2 is more like a prefabricated apartment you place inside an already existing house. With a Type 2 hypervisor, you first have a regular operating system on your computer like Windows 11 or Mac OS. Then, on top of that operating system, you install the hypervisor software just like you'd install any other application like a web browser or a video game. Programs like VirtualBox or VMware Workstation are perfect examples. You double-click an icon, an application window opens, and inside that window, you can create and run your virtual machines. The advantage here is convenience. Anyone can download VirtualBox for free and start experimenting with a Linux virtual machine on their Windows laptop in minutes. The downside is performance. The Type 2 hypervisor has to go through the host operating system, the Windows or macOS layer, to get to the physical hardware. It's a middleman talking to another middleman. This adds overhead and makes it inherently less efficient than its bare metal cousin. You wouldn't run a global banking system on a Type 2 hypervisor, but it is the absolute perfect tool for developers, students, hobbyists, and anyone who needs to run another operating system on their personal computer without rebooting. So we have this manager, the hypervisor, either sitting on bare metal or running as an app. But how does it perform its magic? How does it actually trick an operating system into thinking it has its own private computer? It all comes down to 3 core tasks: managing the CPU, the memory, and the I/O, the inputs and outputs. Let's start with the CPU, the brain of the operation. How can one physical CPU with, say, 8 cores service 10 different virtual machines that might collectively need 20 virtual cores? The hypervisor does this through a process called scheduling, which is basically an extremely fast-paced game of time sharing. It slices up CPU time into tiny, microscopic slivers, measured in milliseconds. In one sliver, it lets VM number 1 run its calculations. In the very next sliver, it freezes VM 1 and lets VM number 2 run. Then VM 3, then VM 4, and so on, cycling through them thousands upon thousands of times per second. It happens so blindingly fast that from the perspective of each virtual machine, it feels like it has the CPU's undivided attention. It's like a grandmaster chess player playing 20 games at once, moving from board to board so quickly that each opponent feels like they're in a one-on-one match. To make this even faster, modern CPUs from Intel and AMD actually have special hardware features, called Intel VTX and AMD V, built directly into the silicon. These are like special instructions that give the hypervisor a direct, high-speed lane to manage these time slices, making the whole process incredibly efficient. Next up is memory, or RAM. This is where security becomes paramount. You absolutely cannot have the virtual machine running your banking software be able to peek into the memory of the virtual machine you're using to test suspicious downloads. The hypervisor enforces this with an iron fist. When you create a virtual machine, you assign it a specific amount of RAM, let's say 4 gigabytes. The hypervisor goes to the physical pool of RAM in the computer, carves out a 4 gigabyte chunk, and dedicates it to that VM. But it does something more clever. It creates a virtual memory map. The guest operating system inside the VM thinks it's writing to memory addresses from 0 to 4 billion. But in reality, the hypervisor is intercepting every single one of those requests and translating them. It's like a post office box. The VM sends a letter to PO Box 123. The hypervisor takes that letter and redirects it to the actual physical address at 456 Elm Street. The VM never knows the real physical address, and the hypervisor builds a virtual wall around that block of memory, ensuring no other VM can ever read or write to it. It gives each VM a completely private, sandboxed memory space. Finally, we have input-output, or I/O. This is how the VM talks to the outside world, to the hard drive, the network card, the keyboard, and the mouse. The hypervisor manages this through a process of emulation and redirection. When your Ubuntu VM wants to save a file, it doesn't write to your physical hard drive. It writes to what it thinks is a hard drive. In reality, that virtual hard drive is just a single giant file sitting on your host computer's hard drive, a file that might be named ubuntuvm.vdi. The hypervisor manages all the read and write operations to this container file. When the VM wants to connect to the internet, it sends a request to what it thinks is a physical network card. But it's a virtual emulated card created by the hypervisor. The hypervisor then takes that network traffic and passes it through the computer's real network card, acting as a sort of mini-router. It intercepts every request destined for hardware, and either emulates a virtual version of that hardware or safely passes the request along to the real deal. So the hypervisor is this tireless, invisible translator, sitting between the virtual worlds and the physical one. It's a CPU scheduler, a memory security guard, and a hardware traffic cop, all rolled into one incredibly sophisticated piece of software. And while that sounds incredibly complex, the world of virtualization actually splits into 2 main philosophies, 2 distinct camps for how this magic trick is performed. It all comes down to a single critical question. Where does the hypervisor live? Does it sit directly on the raw physical hardware, or does it live inside another operating system like an app? The answer to that question defines the 2 types of hypervisors, Type 1 and Type 2. Let's start with the heavyweight champion, the one that powers the entire modern internet, the Type 1 hypervisor. You'll also hear it called a bare metal hypervisor, and that name tells you everything you need to know. Imagine you just bought a brand new powerful server. It's a blank slate of silicon, metal, and plastic. With a Type 1 hypervisor, the very first thing you install before anything else is the hypervisor itself. It goes directly onto the bare metal of the hardware. There is no Windows, no macOS, no Linux underneath it. The hypervisor is the foundational operating system. Think of it like building a massive apartment complex. The physical hardware, the CPU, the RAM, the storage, is the plot of land and the concrete foundation. A Type 1 hypervisor is the master architect and construction foreman who builds the entire complex directly on that foundation. It lays out the plumbing, the electrical, the structural supports, and then it builds each individual apartment, each virtual machine with direct access to those core utilities. Because the hypervisor is the first and only layer communicating with the hardware, it's incredibly efficient. There's no middleman, no translation layer slowing things down. This direct line to the hardware means you get maximum performance, rock-solid stability, and enhanced security. This is why Type 1 hypervisors are the undisputed kings of the data center. When companies like Amazon, Google, or Microsoft build their colossal cloud platforms, they are using Type 1 hypervisors. Every time you spin up a droplet on DigitalOcean or an EC2 instance on AWS, you are summoning a virtual machine managed by a bare metal hypervisor. It's what allows them to safely and efficiently pack hundreds of different customer servers onto a single physical machine, all while keeping them completely isolated from one another. This is enterprise-grade stuff. We're talking about products like VMware's ESX, Microsoft's Hyper-V, and the open-source KVM, which is the backbone of many cloud providers. They are built for one purpose: to run virtual machines at scale with the best possible performance. But what if you're not a multi-billion-dollar corporation? What if you're just a developer, a student, or a curious tinkerer who wants to run Linux on your Windows laptop? You're not going to wipe your entire computer just to install a bare metal hypervisor. That would be like demolishing your family home just to build an apartment for a temporary guest. It's complete overkill. And that's where the second camp comes in, the Type 2 hypervisor. A Type 2 hypervisor is also known as a hosted hypervisor. And again, the name is a perfect clue. This type of hypervisor runs as a standard application on top of your existing operating system. You have your Windows PC or your MacBook. You use it every day for browsing, email, and work. Then, you decide you want to try a virtual machine. You simply go online, download a program like VirtualBox or VMware Workstation, and install it just like you would install Google Chrome or Microsoft Office. To go back to our building analogy, if your main computer and its operating system are your fully furnished house, a Type 2 hypervisor is like a self-contained in-law suite that you build inside one of your spare rooms. Your house, the host OS, is still running everything: the lights, the water, the heating. The in-law suite, the virtual machine, is just a guest. It gets its resources, its electricity, its water by asking the main house for them. It doesn't have a direct connection to the city's power grid. It has to go through the house's main breaker panel. This hosted approach has one massive advantage: convenience. It's incredibly easy to get started. Within minutes, you can have a completely different operating system running in a window on your desktop. It's the perfect tool for developers who need to test their software on different platforms without owning a dozen different computers. It's fantastic for cybersecurity researchers who want to analyze a suspicious file in a safe, sandbox environment where, if it turns out to be a virus, it can't harm their actual computer. It's a lifeline for anyone who needs to run a single critical piece of legacy software that only works on, say, Windows XP. You just create a little Windows XP virtual machine and run that one program inside it safe and sound. Of course, there's a trade-off. Because the Type 2 hypervisor has to go through your main operating system, the host, to get to the hardware, there's a layer of overhead. The requests from the virtual machine have to be translated by the hypervisor, then passed to the host OS, which then finally talks to the physical CPU and RAM. This extra step makes Type 2 hypervisors inherently a bit slower and less efficient than their bare metal counterparts. So, Type 1 versus Type 2 isn't about which one is better. It's about which one is the right tool for the job. It's the difference between a professional, purpose-built race car and a reliable family sedan. The Type 1 hypervisor is the race car. It's stripped down, ridiculously fast, and designed for one thing only: winning the race for performance and efficiency on the professional track of a data center. You wouldn't use it to go get groceries. The Type 2 hypervisor is the family sedan. It's comfortable, versatile, and incredibly convenient for everyday tasks. You can take it anywhere, it's easy to drive, but you're not going to set any lap records with it at the Monaco Grand Prix. Understanding this distinction is key. The cloud is built on Type 1. The personal desktop virtualization that most of us first encounter is Type 2. One is for industrial-scale production. The other is for personal-scale development, testing, and convenience. They are two different solutions to two different problems, both leveraging that same core magic of the hypervisor. So now we have our physical machine, the host. We understand the brilliant software layer, the hypervisor, that acts as the manager. And we know the two main ways it can be installed, either directly on the bare metal or hosted as an application. We've assembled all the key components. The stage is set. The only question left is, what actually happens when you press the start button? What is the step-by-step process that takes these abstract concepts and forges them into a living, breathing virtual computer that appears on your screen? It's a process of digital creation, a boot-up sequence that happens entirely in software, and it's where the true magic begins. So let's walk through that creation, that digital birth. Imagine you are an architect, but instead of designing a house of brick and mortar, you're designing a computer made of pure information. Your drafting table is the software, a program like VirtualBox or VMware, and you're about to draw up the blueprints for your new virtual machine. The first question the software asks is, what kind of computer are you building? This is where you name your creation and, most importantly, tell the hypervisor what operating system it will eventually run. Are you building a Windows 11 machine? A specific flavor of Linux like Ubuntu? Or maybe even an older, nostalgic version of macOS? This choice is critical because it's like telling a car factory whether you're building a sports car or a pickup truck. The hypervisor uses this information to pre-select the best default settings, tuning the virtual hardware to be perfectly compatible with the future software soul of the machine. Next, you move to the foundation of the house, the processor. Your physical computer, the host, might have a powerful CPU with, say, 8 cores. Think of these cores as 8 expert workers on a construction site. The hypervisor asks you, how many of these workers do you want to loan to this new virtual project? You can't give them all away, of course, because your main computer still needs workers to run its own operations. But you can assign 1, 2, or maybe even 4 of those cores to be dedicated to the virtual machine whenever it's powered on. These workers will exclusively handle all the thinking, calculating, and processing for your new VM. The more workers you assign, the faster and more responsive your virtual computer will be, but the fewer workers your main computer has for its own tasks. It's a balancing act, a careful allocation of resources. Then comes the workbench, the short-term memory, or what we call RAM. Your host computer has a certain amount of physical RAM, let's say 16 gigabytes. This is its total workspace for juggling active programs. The hypervisor now asks, how much of this workspace should we reserve for the virtual machine? If you give it 4 gigabytes, then whenever that VM is running, a 4 gigabyte section of your physical RAM is walled off and becomes the exclusive property of the VM. It's the VM's personal desk where it can lay out all the tools and files it's currently using. A bigger desk means it can handle more complex tasks at once without slowing down. But again, every square inch of desk space you give to the VM is space your host computer can no longer use. This is why you can't just create a super-powered VM on a low-powered laptop. You can only give what you have. Now for the storage, the closets and filing cabinets of our virtual house. This is the virtual hard disk. Here, the hypervisor performs a particularly clever trick. It doesn't need to take over a whole physical hard drive. Instead, it creates a single massive file on your host computer's hard drive. This one file, which might be 50 or 100 gigabytes in size, acts like a digital container. To the virtual machine, this file is its hard drive. It sees it as a completely separate, empty disk, ready for an operating system, programs, and files. To your host computer, it's just another file, one it can move, copy, or delete like any other. You're even given a choice on how this storage is created. You can make it a fixed size, where that 50 gigabyte file is created immediately, taking up all that space from day one. This is like building a large, empty warehouse. It's fast to use because the space is already there. Or you can choose dynamically allocated. This is more like starting with an empty folder that grows in size only as you add files to it. It saves space initially, but can be a little slower as the VM has to constantly ask the host to expand its container file. So there you have it. The blueprint is complete. You've defined the CPU, the RAM, and the hard drive. You've created a complete, technical specification for a computer that doesn't exist. It's a ghost in the schematics. The next step is to provide the building materials. The blueprint is useless without them. In the world of virtual machines, the primary building material is an ISO file. An ISO file is a perfect digital replica of an installation CD or DVD. Remember when you used to buy Windows in a box with a shiny disk inside? An ISO file is that disk converted into a single convenient file you can download from the internet. It contains the entire operating system, all the installers, drivers, and initial software, all packed and ready to go. You point your hypervisor to this ISO file. You're essentially telling it, here are the flat-packed boxes of parts. Use the blueprint we just designed and start building. And then you click the Start button. This is the moment of creation. A new window appears on your screen, and inside that window, something incredible happens. You see a black screen with white text, just like a real computer booting up for the very first time. You're seeing a virtual BIOS, a software simulation of the firmware that kicks off the boot process on a physical machine. This virtual BIOS sees the virtual hard drive you created, it sees the virtual RAM you allocated, and it sees the virtual CD drive, which you've digitally inserted the ISO file into. The hypervisor, acting as the master builder, instructs the virtual machine to boot from that ISO file. And just like that, the Windows or Linux installer whirs to life inside the window. You're now looking at a computer within a computer. You interact with the installer using your mouse and keyboard, but the hypervisor cleverly intercepts these signals. When your mouse pointer is inside the VM window, the hypervisor passes its movements to the virtual machine's operating system. When you click, the VM thinks it's receiving a click from its own virtual mouse. As you go through the installation steps, choosing a language, partitioning the virtual hard drive, creating a user account, you are laying the digital foundation. The installer copies files from the ISO image onto the virtual hard drive file, slowly but surely giving your ghost a form, a personality, an operating system. But there's one more crucial piece of the puzzle. How does this new computer talk to the outside world? How does it get on the internet? The hypervisor acts as a master network engineer, offering a few brilliant options. The most common and simple is called NAT, or Network Address Translation. With NAT, the virtual machine essentially hides behind your host computer. It borrows your host's internet connection. To the outside world, any internet traffic from your VM looks like it's coming directly from your main computer. The hypervisor acts as a traffic cop, routing requests from the VM out to the internet and directing the responses back to the correct window. It's simple, secure, and works right out of the box. A more advanced option is bridged mode. In this setup, the hypervisor makes the virtual machine appear as a completely separate, physical device on your home network. Your Wi-Fi router will see your laptop, your phone, and this new virtual machine, and it will give the VM its very own unique IP address. This is incredibly powerful if you want to run a server or a service on the VM that other computers on your network need to connect to directly. Once the installation is complete and the networking is configured, the virtual machine reboots. But this time it doesn't boot from the ISO file. It boots from its own virtual hard drive, where a fresh new operating system now lives. And then you see it. The iconic Windows desktop, the clean macOS login screen, or the powerful Linux command line, all materializing inside that window. You have done it. You have taken a piece of your computer's hardware, drawn a digital fence around it, and used a software blueprint to construct a fully functional, independent computer inside of it. We've built our digital phantom, a ghost in the machine, but this ghost can do real work. So what happens when we unleash it? What are the real-world missions we can send this virtual computer on? From creating sterile cybersecurity labs to building time machines for old software, the practical applications are where this technology transforms from a neat trick into an absolutely indispensable tool. Let's start with one of the most thrilling missions: entering the world of a cybersecurity analyst. Imagine you work for a major tech company, and a suspicious email lands in your inbox. It has an attachment, a file named quarterly_report.exe. Now your every instinct is screaming trap. This could be ransomware, a keylogger, a virus that could cripple your entire company's network. In the old days, you'd need a completely separate, physically isolated computer and air-gapped machine to even think about opening this. You'd have to buy it, set it up, and keep it totally disconnected from everything else. It's slow, it's expensive, and it's a pain. But with a virtual machine, the game changes completely. You simply spin up a fresh, clean VM. Let's say a basic Windows 10 instance. This virtual machine is a pristine, disposable digital laboratory. It exists as a file on your powerful host computer, But thanks to the hypervisor, it is completely walled off. It has no access to your personal files, your company network, or even your physical hardware in any meaningful way. It's living in its own little pocket universe. Now you drag that suspicious quarterly_port as a file into the virtual machine, and you double-click it. You hold your breath, and the malware goes wild. A fake ransomware notice pops up. Files on the VM's desktop start encrypting themselves, and network monitoring tools show it trying to call home to a shadowy server in another country. You, the analyst, are watching all of this from the safety of your host operating system, like a scientist observing a deadly virus through the thick glass of a biocontainment lab. You can take notes, analyze the malware's behavior, see what files it creates, what network connections it attempts. You can learn its secrets. And when you're done, when you have all the information you need to create a defense against this threat, you don't need an antivirus. You don't need to reformat a drive. You just click one button. Delete virtual machine. Poof! In an instant, the entire infected operating system, the malware, every trace of its existence is gone. It's like taking that biocontainment lab and the virus inside it and incinerating it into digital ash. Your host computer was never, for a single second, at risk. This concept is called sandboxing, and it is a cornerstone of modern cybersecurity. It allows researchers to safely detonate digital bombs every single day to learn how to disarm them. But let's shift gears from the high-stakes world of cyber defense to the equally complex world of creation. Software development. If you've ever wondered why your favorite app on your iPhone works just as well on your friend's Android, or why a website looks perfect on Chrome, Firefox, and Safari, you have virtual machines to thank. Imagine you're a developer building a new piece of software. You need to make sure it works for everyone. That means testing it on Windows 10, Windows 11, the latest version of macOS, maybe a few older versions too, and of course several different flavors of Linux like Ubuntu and Fedora. Without VMs, your office would look like a computer museum. You'd need a dozen different physical machines, each with a different operating system, cluttering up your desk, sucking down power, and generating a ton of heat. Every time you made a small change to your code, you'd have to run around to each machine and test it. It would be a nightmare of inefficiency. With virtual machines, that entire computer museum is condensed into a single powerful desktop or laptop. A developer can have a Windows 11 VM, a macOS VM, and an Ubuntu VM all running simultaneously, side by side in different windows on their screen. They can write code on their main machine, and then instantly test it in all these different environments without ever leaving their chair. But here's where it gets even more magical. Let's say you're testing the installation process for your new software. You run the installer inside your Windows 11 VM, and something goes horribly wrong. It crashes the virtual operating system or installs files in the wrong place or just makes a complete mess. On a physical machine, you'd have to spend the next hour uninstalling everything, cleaning the registry, and trying to get the computer back to its original state. With a VM, you use a feature called snapshots. Before you ran the installer, you took a snapshot. A snapshot is an exact, instantaneous picture of the entire state of the virtual machine at that moment, the memory, the hard drive, everything. It's a save point just like in a video game. So after the installation disaster, you don't panic. You just click Revert to Snapshot. In about 3 seconds, the virtual machine is instantly transported back in time to the exact moment before you ever ran the installer. The mess is gone. The error never happened. You're ready to try again. This ability to instantly undo catastrophic changes is a developer's superpower. It allows for fearless experimentation and dramatically speeds up the process of creating reliable, stable software for all of us. Now let's take that time-traveling concept one step further. What about running old software that's completely incompatible with modern computers? Maybe it's a classic video game from your childhood that only ran on Windows 98. Or maybe it's a critical piece of business software that was custom-built for your company 20 years ago and only works on Windows XP. You can't run it on your new Windows 11 machine. The code is just too old. The traditional solution was to keep an ancient, dusty, yellowing computer tower humming away in a closet somewhere, just for that one program. It's unreliable, it's a security risk because it can't be updated, and it's just waiting for a hardware failure to die forever. A virtual machine is the ultimate act of digital preservation. You can create a Windows XP virtual machine on your modern, high-performance laptop. You install that old critical software inside it, and it runs perfectly just like it did back in 2003. It's completely oblivious to the fact that it's not on real hardware. It's living in a perfectly simulated time capsule. That virtual machine is just a file. You can back it up, copy it, move it to a new computer in 10 years. That critical piece of software or that nostalgic game is now future-proofed, preserved in a digital amber that will run on hardware that hasn't even been invented yet. Finally, let's zoom out from our personal computers and look at the backbone of the internet itself. Go into any large company's data center, or what used to be their data center, and you'll find the most profound use case of all: server consolidation. In the early days of the internet, the rule was one application, one server. Your company's email ran on one physical server. The company website ran on another physical server. The file database ran on a third. This led to something called server sprawl. Companies had racks upon racks of physical servers, each one a big, power-hungry, heat-generating box. The crazy part? Most of these servers were incredibly underutilized. The email server might only be using 10% of its processing power. The web server might be sitting idle 95% of the time. It was a colossal waste of money, electricity, and physical space. Virtualization turned this model on its head. Instead of buying dozens of medium-powered servers, a company could buy one or a few incredibly powerful physical servers. Then, using a hypervisor, they could slice up that one powerful machine into dozens of smaller, independent virtual servers. That one physical box could now host the email server VM, the web server VM, the database VM, and 20 others, all running simultaneously. Suddenly, server utilization jumped from 10% to 80% or 90%. The electricity bill was slashed. The amount of physical space needed for the data center shrank dramatically. This revolution in efficiency is what paved the way for modern cloud computing. When you rent a server from Amazon Web Services or Microsoft Azure or Google Cloud, you're not renting a physical box. You are renting a virtual machine that is running on one of their massive, hyper-efficient physical servers, sharing resources with hundreds of other VMs. They are simply taking this concept of server consolidation and applying it at a planetary scale. From protecting your computer, to building your favorite apps, to preserving the past and powering the very fabric of the modern internet, these isolated worlds within a world have become one of the most fundamental and transformative technologies of our time. But as with any revolutionary technology, the story doesn't end there. For all their power, for all their world-changing impact, virtual machines have a fundamental built-in trade-off: a hidden cost. To understand it, let's go back to our house analogy. Building a VM is like building a complete, brand new house on your property. It has its own foundation, its own plumbing, its own electrical grid, its own roof. It's fully self-contained and incredibly robust. But building a whole house just to host a dinner party for one night is, well, it's a lot of work. It's expensive, takes up a ton of space, and it takes a while to get everything up and running. This is the central challenge of virtualization. Overhead, every single virtual machine has to run a complete, independent operating system, a full copy of Windows or Linux or Mac OS. This guest operating system has its own kernel, the core engine of the OS, its own drivers, its own libraries, its own background processes, all running on top of your main host operating system, which is also running all of those things. You're essentially running two or more of everything. Two kernels, two sets of system files, two clocks. It's a duplication of effort on a massive scale. Think about it. Your physical computer's processor, its RAM, its storage, they're all being shared. The hypervisor does a masterful job of juggling these resources, but it's still a juggle. Starting a VM isn't instant. It has to boot up just like a real computer, which can take seconds or even minutes. A VM consumes a significant fixed chunk of your RAM and disk space, even if the application inside it is just sitting there, doing nothing. For years, this was just the price of admission. The benefits of isolation and flexibility were so immense that we accepted the overhead. But in the fast-paced world of software development and cloud computing, where companies might need to launch thousands of instances of an application in a matter of seconds to handle a sudden spike in traffic, that overhead started to look less like a price and more like a bottleneck. The world needed something lighter, faster, more efficient. And that's when a new idea and evolution of the concept truly took off. It's a technology you've almost certainly heard of, even if you weren't sure what it was: containers. If a virtual machine is like building a whole new house on your property, a container is like buying a prefabricated high-tech apartment pod. This pod doesn't need its own foundation or its own main power line from the street. It plugs directly into the building's existing infrastructure. It shares the foundation, the plumbing, the main electrical grid. But inside it has its own walls, its own furniture, its own layout, and its own key to the door. It's completely isolated from the other apartments, but it's dramatically lighter and faster to install because it's not duplicating the entire building's infrastructure. This is the genius of containers, with Docker being the most famous example. Unlike a VM, a container does not run its own full operating system. Instead, all the containers running on a single host machine share the kernel of the host's operating system. They share that single central engine. The container itself only packages up the bare essentials that an application needs to run: the app's code and its specific dependencies, the libraries and files it needs to function. That's it. The difference in performance is staggering. Mind-blowing, really. A virtual machine with its full OS might take a minute to boot. A container can start in a fraction of a second. A server that might be able to handle 10 virtual machines before running out of memory could potentially run 100 or even 1,000 containers. It was a quantum leap in efficiency. Suddenly, developers could package their applications into these lightweight, portable containers and know that they would run exactly the same way on their laptop, on a test server, or in the cloud. It was faster, cheaper, and more scalable. So, does this mean virtual machines are obsolete? Are they the dinosaurs and containers are the mammals destined to take over the world? Not at all. And understanding why is the key to understanding the modern technological landscape. It's not a war. It's a division of labor. They solve different problems. The greatest strength of a container, sharing the host OS kernel, is also its most significant limitation. Because they share a kernel, a container provides isolation at the software level. A virtual machine managed by a hypervisor provides isolation at the hardware level. It's a much deeper, more fundamental separation. Think of it as security. The apartment pod is secure. It has a lock on the door. But if someone manages to compromise the entire building's foundation, all the apartments are at risk. The separate house with its own foundation is a fortress. If you need to run an application that you don't fully trust, or you have extremely high security requirements where a potential breach absolutely cannot be allowed to affect anything else on the system, a virtual machine is still the undisputed champion. It's the digital equivalent of a maximum security prison. There's another crucial difference: operating systems. Since containers share the host kernel, you can generally only run containers that are compatible with that kernel. You can run different versions of Linux in containers on a Linux host, but you can't just run a Windows container on a Linux host without some very complex layers in between. With a virtual machine, anything goes. You can run a full Windows 11 virtual machine on your Linux server. You can run a Linux virtual machine on your Windows gaming PC. You can even run a macOS virtual machine on your Windows laptop if you're a developer needing to test an iOS app. That level of cross-platform flexibility is something only VMs can provide. So the modern world uses both, often together. A company might use a big, powerful virtual machine to create a secure, isolated environment. And inside that virtual machine, they might run dozens of fast, lightweight containers to manage their applications efficiently. It's the best of both worlds. The fortress-like security of the VM, with the speed and agility of containers running safely inside its walls. VMs provide the infrastructure, containers provide the application delivery. But technology never stands still. We went from physical machines to virtual machines to get more flexibility. We went from virtual machines to containers to get more speed and efficiency. What's the next step in this journey of abstraction? It's something called serverless computing, or functions as a service. And it's exactly what it sounds like. With serverless, the developer doesn't even think about the container anymore, let alone the virtual machine or the physical server. They just write a small piece of code, a function that does one specific thing, like process an image upload or handle a login request. They upload that function to a cloud provider like Amazon, Google, or Microsoft. And that's it. The cloud provider handles everything else. When a user needs to run that function, the cloud platform instantly spins up an environment, runs the code, and then shuts it down. The developer doesn't manage a server, they don't patch an operating system, they don't even build a container. They just write the code. They only pay for the exact milliseconds that their code is actually running. It's the ultimate evolution. We've abstracted away the hardware with VMs. We've abstracted away the operating system with containers. And now we're abstracting away the container itself, until all that's left is the pure logic of the application. It's a beautiful logical progression that has fundamentally changed how we build and deploy software. We've journeyed from the physical to the virtual, from the monolithic to the microscopic, all in the pursuit of a more efficient, secure, and powerful digital world. We've seen how these virtual worlds are built, why they matter, and what their future looks like. But theory is one thing, experience is another. All this talk of hypervisors, guest operating systems, and digital sandboxes might feel abstract. So what if you could build one yourself? Right now, on the computer you're using to watch this video? What are the tools you need, the steps you take, and the incredible things you can do the moment you launch your very first virtual machine? Well, the incredible news is you can. And it's not some dark art reserved for basement-dwelling hackers or corporate IT wizards. It's accessible, it's free, and the only real price of admission is your own curiosity. Let's break down how you can build your very first virtual machine today using just 2 key ingredients. Think of it like a recipe. First, you need the stage. This is the virtual theater where your new computer will perform. In the technical world, this is called a hypervisor. Now, don't let that word scare you. For our purposes, a hypervisor is just an application, a program you install on your Mac or your Windows PC, just like you'd install a web browser or a video game. Its only job is to create and manage these virtual computers. There are 2 giants in the free beginner-friendly space: Oracle VM VirtualBox and VMware Workstation Player. Both are fantastic, both are free for personal use, and they act as the perfect starting point. Think of them as the digital equivalent of an empty plot of land you've just been given. It's a blank canvas, ready for you to build upon. You download one of these, install it, and you've completed step 1. You now have the stage. Second, you need the actor. You need the operating system itself. You need the Windows or the Linux that's going to run on your new virtual stage. This comes in the form of a single file called an ISO image. Again, fancy name, simple concept. An ISO file is the digital blueprint for an operating system. It's like the entire installation DVD for Windows XP or the classic Mac OS, perfectly preserved and compressed into one file you can download from the internet. So where do you get one? My number 1 recommendation for any beginner is to start with a version of Linux, specifically Ubuntu Desktop. Why? 3 reasons. 1, it's completely free forever. No licenses, no activation keys. 2, it's incredibly user-friendly. If you can use Windows or a Mac, you can use Ubuntu. And 3, it has one of the largest and most helpful communities on the planet. Any question you have, someone has already asked and answered it. You just go to the official Ubuntu website, click download, and you'll get that ISO file. Of course, if you want to run Windows in a virtual machine, you can do that too. You can go straight to Microsoft's own website and download an official Windows 10 or Windows 11 ISO file. Just know that to unlock all its features, you'd eventually need a valid license key, but to just install it and try it out? It's a free download. So now you have your 2 ingredients. You have your hypervisor app like VirtualBox installed, and you have your operating system blueprint, that Ubuntu ISO file, sitting in your downloads folder. Now comes the magic. You open up VirtualBox and you click the big new button. A wizard pops up to guide you. First, it asks for a name. You can call it My First Linux Box, Secret Spy OS, Test Lab, whatever you want. As you type, you'll notice something cool. The software is smart. If you type Ubuntu, it will likely guess, oh, you're installing Linux, and it will pre-select the right settings for you. It'll then ask you to point it to that ISO file you downloaded. Next comes the most important part, allocating resources. Remember, this virtual machine is borrowing power from your real physical computer, so you have to decide how much to lend it. It will ask you about memory or RAM and processors or CPU cores. Here's a simple rule of thumb. Never give it more than half of what you have. If your computer has 16 gigabytes of RAM, lend the virtual machine 4 or maybe 8. If you have an 8-core processor, give it 2 or 4 of those cores. This is not a permanent decision. It's a slider. If the VM feels slow, you can shut it down, move the slider up, and give it more power. If you find you don't need that much, you can move it back down. You are in complete control. Then it will ask about the hard drive. It'll say, create a virtual hard disk now. This sounds intimidating, but all it's doing is creating a single large file on your actual computer that will act as the hard drive for your virtual one. It will live inside a folder, just like a movie file or a document. You can tell it to be a dynamic size, say up to 50 gigabytes. This means it won't take up all 50 gigs right away. It will start small and only grow as you install programs and save files inside your virtual machine. You click Finish, and that's it. You've done it. You have architected a computer. It exists as a name in your VirtualBox library. It has a processor, memory, and a hard drive you defined. It's a ghost waiting to be brought to life. and then you select it and you click the big green start arrow. A new window will open on your screen. But this isn't just any window. It's a portal. Inside, you won't see your normal desktop. You'll see a black screen with white text, just like a real computer booting up for the very first time. It will read that ISO file you gave it, and the Ubuntu installer will spring to life, asking you what language you want to use and where you live. You go through the installation steps, which usually takes about 10 or 15 minutes, and at the end it will reboot. And when it comes back on, you'll see it. A full, glorious Ubuntu Linux desktop, running in a window on your Mac or PC. You can move your mouse into it, and it's controlling the cursor inside Ubuntu. You can click on its web browser, and it will use your computer's internet connection to go online. You can type in its word processor. You can install software inside it. You have a completely separate, fully functional computer, living inside a window. At this point you might be asking, okay, so what? What do I do with this? This is where the universe opens up. This virtual machine is the ultimate sandbox. Have you ever gotten a weird email with a link that looks a little suspicious? Open it inside the virtual machine. If it's a virus that tries to lock all your files, who cares? It's only locking the files inside that fake virtual hard drive file. You can literally just delete the entire virtual machine and it's gone. Your real computer, your actual photos, documents, and banking information remain completely untouched, pristine. It's like having a disposable laptop for doing dangerous things on the internet. It's the ultimate learning lab. You want to learn how to use the Linux command line, the thing you see in every hacker movie? This is how you do it. You can't break your main computer. If you type a command that deletes the entire operating system, it only deletes the virtual one. You can just make a new one in 5 minutes. Want to learn to code? Set up a web server? Practice ethical hacking? This is your private, safe, and free laboratory. It's a time machine. Do you have an old piece of software, maybe a classic video game from the 90s, that just refuses to run on modern Windows 11? You can build a Windows XP virtual machine and run it perfectly, just like you did 20 years ago. You're preserving digital history. And perhaps most profoundly, you're stepping into the same world that powers our entire modern infrastructure. That little Ubuntu VM running on your laptop? The technology behind it, that hypervisor, is the exact same fundamental principle that runs the cloud. When you watch a movie on Netflix or use a service from Google, or buy something from Amazon, you are interacting with applications running on massive, powerful virtual machines in a giant data center. By building one on your own desk, you have gained a fundamental understanding of the architecture of the 21st century. You've moved from being just a user of technology to an architect of it. You've learned that a computer isn't just a physical box. It's an idea, a set of instructions and logical spaces that can be created, duplicated, and destroyed with the click of a button. The barrier between the physical and the virtual is not as solid as you thought. The only thing separating you from this world of endless possibility is a couple of free downloads and a healthy dose of curiosity. So go be curious. Go build something. Go explore.